All right, so today we are going to start our third and final module in this course. We are building up to learning about transformers. And so what we are going to be talking about today is magnetically coupled circuits. And our first subtopic of this section is a look at the concepts of self and mutual inductance. So I can't recall if I've asked you this before, but you guys have had some amount of physics classes and stuff like that, right? Or maybe a physics class. Did you guys cover any E&M theory, electromagnetic theory? Unfortunately. Well, unfortunately, it's all about to come bite you in the ass in this class and then in your 360 class next year. So I do review what you need to know and all that kind of good stuff. And so we're going to talk about a little bit of that right here. So how many of you guys have, I'm not going to ask you if you remember what Ampere's circuital law is, but does that sound familiar? Okay. So what Ampere's circuital law tells us is that if we have a wire carrying a current, then we will have a B field or a magnetic flux density wrapping around the wire. So graphically, I could represent that like this. So I'm just saying that I have some conductor that is part of a larger circuit. That's what this black line represents. And then the dots are saying that there's other things connected so that there's a completed current carrying path. And let's say that my current I of t is flowing in this direction. If we were to apply the right-hand rule, how many of you guys remember what the right-hand rule is? At least one person. You all have right hands. If we put our thumb in the direction of current flow, our fingers will wrap around in the direction of the magnetic field or magnetic flux density. So we should see magnetic flux lines pointing out of the paper above our wire, which I am denoting by a dot. So it's like the head of the arrow coming out of the page at us. And the tail of those magnetic field lines are going to be directed into the page below the wire, right? Where these represent our B field as a function of time, where our magnetic field or magnetic flux density, and I kind of use those two terms interchangeably, is measured in Tesla, where 1 Tesla is equal to 1 Weber per meter squared. And a Weber is a volt second. So a Tesla is a volt second per meter squared. So that's what things look like if we have a long section of wire. Now, what if we had a ring of wire? So if I had a circle of wire like so, and let's say for the sake of argument that our current I of t is flowing counterclockwise around this circular ring, what we would see is that for points internal to the ring, our magnetic field would be directed out of the page due to the right-hand rule, and external to the wire or external to that ring, our magnetic field would be directed into the page, right? So it's still going to wrap around the wire, but now we're going to have a magnetic flux total that is directed out of the page when we're in the region of space that's inside that loop, and we're going to have a magnetic flux that's directed into the page in the region of space that's outside of the loop, right? Where our magnetic flux phi B is simply the magnetic field strength multiplied by the area enclosed by the loop. So we've talked about what the field looks like for a wire, and now we've talked about what happens when we turn that wire into a loop. Now let's talk about what happens when we turn that wire into a coil, which we could think of as just a stack full of loops, right? So let's say that I had a cylindrical core, okay? You're gonna have to bear with my inability to draw here. So I have a cylinder that I'm going to use as a form, and I'm going to wrap a wire around it. Like so. And we have N turns of wire. Okay. So I've wrapped it around this cylindrical form some number of times that is greater than 1, so that I have effectively a stack of N loops on top of each other. And if I pass, let me move the current label over here. If I pass current through that wire, once again, using the right-hand rule, I should have some, or using Ampere's circuit law, I should have some magnetic field lines, and the right-hand rule tells me their direction. So in this case, if we're considering that our current is curling around the coil using our fingers, our thumb is going to indicate the direction of our magnetic field line. That's what the right-hand rule tells us. And so what we should see is on the vertical axis, or the axis of symmetry of this thing, we have a magnetic field line like this. But as we get away from the point of symmetry, we're still going to have vertical lines like so. But we're going to see, what we're going to see is that they turn and wrap back around. Because our magnetic field lines always form closed loops, like so, where once again, these blue lines represent B of T. Okay. So in this particular system, we're going to have a pretty easily and well-defined magnetic flux, because we have a strong B field inside of that coil. And then the area inside of the coil is just the area of one of those loops. So once again, we're going to see that our magnetic flux is just the B field times the area. For the sake of units here, our flux is measured in Webers, where a Weber is a volt second. Okay. The flux linkage of this coil is going to be N times phi B, also measured in Webers. So when we have a coil we have a flux linkage instead of just a simple flux, because the same amount of flux is being generated by every single one of those turns, and they all add together as they pass through the coil. Okay. So our flux linkage for this coil is simply the number of turns times the flux generated by one turn. Well, if we have this coil as part of a linear system, like a circuit, the flux linkage and the current are related to each other by what's called the self-inductance of the coil. Right? So we could say that our flux linkage lambda will be equal to L times I of t, where this L is the self-inductance measured in henries, where 1 Henry is 1 volt second per ampere. So this is the exact same thing as the inductors that you would put in a circuit. They're literally just coils of wire. So we're more formally explaining what an inductor is. And we've gotten to the point of describing the concept of self-inductance, where our coil of wire is generating some, or excuse me, is carrying some current, which generates a flux that passes through the same coil that is carrying the current. Okay, so self-inductance is the flux generated by I1 is passing through coil 1. Okay. Faraday's law of electromagnetic induction. How many of you guys have heard of that? All right. So Faraday's law of electromagnetic induction says that if my flux is changing or my flux linkage is changing, then I am going to induce a voltage. So if our current is time varying, our flux is time varying. Therefore, we should induce a time varying voltage across the terminals of our coil, where this induced voltage, V of t, is given by the derivative of our flux linkage with respect to time. So that is simply the derivative of L times I of t. And if we're assuming that our inductance doesn't change, we get L di by dt. This is literally the exact same equation as the voltage drop across an inductor, because it's exactly what we are describing here. So this is a very abridged review of the concept of self-inductance. So what we're going to talk about next is mutual inductance. So I'm going to draw a simple circuit here. So let's say that I have some time varying source. It literally doesn't matter if it's a voltage source or a current source, which is why I'm not specifying what it is. And I connect that source to a coil. Like so. Such that some current I1 of t will flow through what I'm going to call coil 1. And I'm going to specify here that coil 1 has N1 turns. we should expect to see an induced voltage V1, where V1 is nothing more than L1 di1 by dt, where L1 represents the self-inductance of coil number 1, okay? I've just redrawn our little coil from a moment ago in a more circuit-like form, okay? So if we're going to talk about mutual inductance, that means we need a second coil. So what if I had a separate coil of wire over here? I'm not going to connect it to anything just yet. What should we expect to see? I mean, potentially, yes, but that's not where we're worried more about the electrical characteristics of what's going on right now, right? So what I should expect to see in this system is that coil 1, because it's carrying a current, we're going to have some flux here, which I'm going to call phi 1,1, because it's the flux through coil 1 caused by current I1. And then I'm also going to have some flux, let's call it phi 1,2. So it's produced by coil 1 and passing through coil number 2. So that's where those subscripts come from, right? I'll do you one better. I'll write it down. So phi 1,1 is the flux produced by coil 1 that passes through coil 1, and phi 1,2 is the flux produced by coil 1 that passes through coil 2. So if we have two coils in close proximity to each other, and one of them is carrying a time varying current, what we are going to see is that a time varying voltage will be induced in the second coil, okay? So these two systems are what we call magnetically coupled, okay? So because the current I1 of t is changing, it is producing a time varying flux and a time varying flux linkage. That time varying flux is passing through coil 2. And whenever a coil experiences a time varying flux, a voltage is induced in the coil, according to Faraday's law of induction. So we should see, actually, let me specify this a little bit here. This is coil 2, and it has N2 turns, okay? So what we should see is some voltage drop across our second coil due to the time varying flux produced by coil 1 that is passing through coil 2. We can mathematically describe this voltage as V2 of t will be the derivative of our flux linkage for coil 2 with respect to time. So what do you guys think the flux linkage for coil 2 is supposed to be? So how did we define flux linkage up here? The number of turns times the flux, right? So coil 2 has N2 turns, and the flux passing through it is flux 1, 2, right? Well, if we look at these two relationships here, right, we could see that we could rewrite phi b in general as so let me, sorry, I'm having trouble doing the algebra in my head here, so let me write it out specifically. So if we have n times phi b is equal to L times I, then phi b would be L over N times I, right? So this is going to look like the derivative with respect to time of N2 times L1, the inductance of coil 1, divided by the number of turns in coil 1 times the current passing through coil 1. Because our current I1 is the thing that's generating the flux, right? I'm going to come down here because I'm running out of room up there. And I'm simply going to take all my constant terms to the outside of that derivative because they're constant. I can do that. And so that's going to look like N2 divided by N1 times L1 times the derivative of I1 with respect to time. And we are going to call this M21 times the derivative of I1 with respect to time, where this M21 thing here is the mutual inductance of coil 2 induced by current I1. Okay. So I want to be really, really clear about this. Go back to my picture. These two networks are not physically connected in any way, shape, or form. Okay. There's no wire connecting coil 1 to coil 2 whatsoever. But because of what's happening in coil number 1, we are observing a voltage in coil number 2. And the voltage that we are observing in coil number 2 depends on the rate of change of the current flowing through coil number 1, because that's what that derivative relationship means, the rate of change, right? So we are seeing an induced voltage across the terminals of coil number 2 because of the time varying current flowing through coil number 1. And we have mathematically described both the voltage drop induced across coil number 1 due to its self-inductance, and we have described the voltage drop induced across coil number 2 due to the mutual inductance between the two coils. Okay. So what do you guys think would happen if I moved my source from being connected to coil 1 to being connected to coil 2? Yeah, it's effectively the exact same thing, right? So if we reverse the roles. Coil 1 and coil 2 by applying our source coil 2, we would induce the following voltages. So what we would get is that the voltage drop across coil 2 would only have a self-induction term. So that would look like L2 times the derivative of I2 with respect to time. And the voltage induced across 1 would be the derivative of the flux linkage of 1 with respect to time, which is going to come out looking like, after effectively the exact same algebraic steps here, N1 over N2 times L2, the derivative of I2 with respect to time, which we would call M12, DI2 with respect to time. Very similar results when we move the source from the left-hand coil to the right-hand coil and figure out what's going on. Okay. Well, as it turns out, M12 and M21 will literally be the exact same quantity because the energy has to be conserved both ways. So we are now going to say that M12 is equal to M21 is equal to just M, where this M represents the mutual inductance seen between the two coils. And we can just use a single value because it does not matter in any way, shape, or form which of our two coils is the one that we are exciting and the other one's the one that's being induced or having a voltage induced across it. Any question thus far? All fairly okay. All right. So now let's talk about what happens if we put a source on both coils. So if I had a system like this, where I have N1 turns on coil number 1, and coil number 1 is carrying some current I1 of T. And then I have a second coil, like so, where my second coil has N2 turns and is carrying a current I2 of T in this direction. And we have some source over here. We are going to have some flux phi11. We are going to have some flux phi22. So that's taking care of why we're going to have an induced or self-induced voltage term. And then we're also going to have this flux shared between the two coils, which means we're going to have a mutual inductance term on both voltages as well. Okay. So for a system like this, the flux linkage of coil 1 is going to be L1 times I1 of T plus M times I2 of T. And the flux linkage for coil 2 is going to be L2 times I2 of T plus M times I1 of T. These flux linkages are going to cause voltages V1 and V2 to be induced across their respective coils. So here is V1 with the correct polarity. Here is V2 with the correct polarity, where V1 is the derivative of flux linkage 1 with respect to time for L1 DI1 plus M DI2. And similarly, let me move this down so that I'm not running into my own writing. We're going to have the derivative of flux linkage for coil 2 is going to give us L2 DI2 with respect to time plus M DI1 with respect to time. So for each of these voltage expressions, we have a self-induced term, and we have a mutually induced term, right? And that's because current flowing through I1, or excuse me, the current I1 that's flowing through coil 1 generates a flux that passes through coil 1 and a flux that passes through coil 2. And similarly, the current that's flowing through coil 2 develops a flux that passes through coil 2 and a flux that passes through coil 1. So these two systems are coupled to each other through that mutual inductance term, right? So these are the concepts of self-inductance and mutual inductance. How do you guys feel? Conceptually, does anything seem off? I'm not trying to trick you. I'm genuinely asking a question. Yes. Yes, so L is the value of the inductance, right? Measured in henries. So what do you think M is measured in? Look at the math. It's also got to be in henries. Yeah, so the mutual inductance is also in henries. Yep. And it just represents the interaction between those two coils that are close to each other. So doesn't matter if it's self-inductance or mutual inductance, it's measured in henries. Okay. Any other questions? Sorry, what? Okay, so we'll get to that in a minute. But so before we work with numbers, actually, that's bringing us to our next thing. We are going to establish what's called the dot convention. Because as you can see, these graphs like this, where we're keeping track of all the flux and stuff like that, are going to get real busy and real messy pretty quick. Okay. So in order to clean things up for drawing and analyzing schematics, we utilize a dot convention, okay? And I am not gonna lie to you, this part can be a bit confusing. So I'm gonna go through it slowly. If you have any questions, please ask, and then I'm going to summarize things with a couple of pictures that you should very much like put on your equation sheet or something like that for the next test, because they pretty much tell you everything that's going on in any configuration that I could give you, okay? So what our dot convention allows us to do is take the funny looking diagram that I just drew when I'm redrawing it here. There, this is I1 and V1, and this coil is excited. This is I2 and V2, and replace it with this. So make sure I have enough room here. This is only going to be big for the way that I'm drawing it right now, so I can define the voltage very specifically. So we know that the voltage drop across coil 1 is going to be L1 di1 by dt plus M di2 by dt. So let's put just some inductance L1 here. And what I'm going to do is I'm going to put a dot here. And I'm going to define my current I1 of T is flowing into the dotted terminal of that first coil or that first inductor. And then over here, I'm going to have effectively the exact same thing. This is coil 2. This is my dot. And now I'm drawing the other side of the circuit in the same way. So this is going to look like L2 di by dt plus M di1 by dt is equal to V2 like so. And we represent the mutual inductance between the two coils by literally defining what M is and pointing to the two coils that are coupled together, okay? So we no longer have to keep track of where the flux is flowing, the direction of the flux, and all of that kind of good stuff. What we're really going to be keeping track of now, excuse me, is the direction of the current, whether it's flowing into the dotted terminal or into the undotted terminal, and whether we have defined the positive polarity volt of the voltage as the same as the dotted terminal or the undotted terminal, okay? So we're going to go through the rules here. The signs on the self and mutual terms of the induced coil voltages depend on the direction of current flow. So here's our first rule for figuring out how to assign these plus and minus signs here, okay? The self-induced component of V1 is assigned a positive sign if condition A, the positive polarity of V1 is at the dotted terminal, and both of these conditions need to be true. I1 enters coil 1 at the dotted terminal. We'll talk about the second condition first, but I want to show you guys something here. So the positive polarity terminal of our voltage V1 is literally at the exact same node as the dotted terminal, okay? So the positive polarity terminal of V1 is at the dotted terminal. So that's the first part of that first statement. That is true. And we can see that our current I1, as it flows along this path in this clockwise direction, that current I1 is flowing into the dotted terminal. So both parts of this first condition are true, which is why this term has a plus sign, or it's positive, okay? The second condition that will get us a plus sign for the self-induced component of V1 is that the positive polarity terminal of V1 is at the undotted terminal. And I1 of T enters coil 1 at the undotted terminal. So it's literally the exact opposite of what we have here. So if the positive polarity terminal were down here and the current were flowing in this direction, that first term would have a positive sign as well. So it's either or, all right? So what if the positive polarity of our voltage were here and the current were flowing this way? The positive polarity terminal is associated with the dotted terminal, but now the current is flowing into the undotted terminal. Neither of those conditions are true, which means we have to give that term a negative sign. Okay. So if either of these are true, it gets a plus. If neither of them are true, it gets a minus. Pretty straightforward, right? All right. So now, since we know what's going on for this self-induced portion, we're going to talk about the mutually induced portion. Okay. So the mutually induced component of V1 of t is assigned a plus sign if, now we're going to have a similar set of conditions here. The plus polarity terminal of V1 of t is at the dotted terminal and I2 enters coil 2 at the dotted terminal. So let's look at that really quickly here, just so that we're all on the same page. So what we're checking for is that the positive polarity terminal for V1 is at the same node as the dot for coil 1, and we're checking to see if the current I2 flows into the dot for coil 2. So because it's a mutual term, we have to be looking at information on both coils, okay? So if the positive polarity is associated with the dot on coil 1 and I2 is flowing into the dot on coil 2, we have a positive sign here. We will get the exact same result for the exact opposite case, just like we saw before. Okay. So if the positive polarity of V1 is at the undotted terminal, and I2 enters coil 2 at the undotted terminal, we'll also have a positive sign for the mutually induced term, right? So that condition would be something like this. If we had the positive polarity of our voltage defined down here, and our current I2 were flowing in the opposite direction as we had previously stated, we would wind up with a positive M term here. If neither of these criteria are met, we give it a negative sign. Sorry, that should be a V1. So we define everything here for the self-induced part and the mutually induced part of voltage V1. The exact same rules apply for voltage V2 if you replace every subscript 1 with 2 and every subscript 2 with 1 in what we just defined. So it's literally the exact same rules, just change the subscripts. So what may be a little bit easier way to process what these rules mean is by me drawing this picture, okay? So if we have two magnetically coupled coils, right? So here is L1, I'm going to put the dot here. Here is L2, I'm going to put the dot here. And these can both be part of larger circuits. I'm going to define V1 as L1 di1 by dt plus M di2 by dt, and my current flowing in this direction. Similarly, I'm going to say that V2 is L2 di2 by dt plus M di1 by dt, and my current I2 is flowing in this direction. So this is effectively a generic case of if the dots are on the same side, which is what we're going to see sometimes. Change this plus to minus if I1 is counterclockwise. So if I1 is actually flowing in the opposite direction, because we're going to choose the direction, we'll get to that in a moment, we would put a minus sign out front. We'll change this plus to minus if I2 is clockwise. On this side, we change the plus to minus if I2 is counterclockwise, and we change this plus to minus if I1, sorry, this one should be clockwise, this one should be counterclockwise. We may also have the case where we see that our dots are on opposite sides. And excuse me, I forgot to explicitly state that these two are coupled. So if our dots are on opposite sides, I will have V1 is equal to positive L1 di1 by dt minus M di2 by dt. And essentially the same thing over here. L2 di2 by dt minus M times di1 by dt. And we are going to change this plus to minus if I1 is counterclockwise. We're going to change this minus to plus if I2 is clockwise. Change this plus to minus if I2 is counterclockwise. Change this minus to plus if I1 is counterclockwise. So that's all those rules summarized for really the two different conditions that we can have. Dots are on the same side and dots are on the opposite side. So let's take these rules and apply them, right? So the first thing that I want to do is just a little exercise from a textbook. So let's say that I have the following configuration. Does not matter what's connected here. I'm defining my voltage V1 of t like so. Here is coil 1. I'm putting a dot on bottom, and I am defining current I1 like so. And then over here, I have my second coil. Dot is on bottom. Here's the direction of my current I2. Here's where I'm applying my voltage, or excuse me, this is where we're figuring out what our voltage V2 is. I want us to define V1 and V2 in terms of L1, L2, and M based on this configuration. So all we're doing is trying to apply the rules and figure out what's what. Okay. So anybody have any thoughts? So there, in my opinion, there are two ways that we can approach this. Okay. So the first way that we could approach this would be to literally flip that first or the left-hand circuit upside down, because the voltage is defined positive polarity on the bottom. We don't really have anything like that in the pictures that we have. Now we can definitely handle it if we look at the text rules, right? So let's do it with the text rules that we developed first, and then let's see what happens if we flip it over and look at the picture, right? So we're going to have V1 of t is equal to L1 di1 by dt, and then we're also going to have a term M di2 by dt, and we don't know what either of those signs are right now. So is the positive polarity terminal of the voltage on the same side as the dot? Yes, for V1, absolutely, okay? Is the current I1 entering the coil at the dotted terminal? No. So that means we're going to get a negative sign. All right. Is the positive polarity terminal of V1 at the dotted terminal? Yes. Is I2 entering the coil at the dotted terminal? No. So this one's also going to get a negative sign. That's it. Now we look at V2. Right? So we're going to have an L2 times di2 term over dt, and then an M times di1 term over dt. All right. So is the positive polarity terminal of V2 at the dotted terminal? Nope. Okay. So the positive polarity of V2 is at the undotted terminal. Is the current of I2 entering the undotted terminal? Yes. So that means we're going to have a plus sign. All right. So for the mutually induced component, we already know that the positive polarity terminal is associated with the undotted terminal. Excuse me. So now we need to check, is I1 entering coil 1 at the undotted terminal? So that means we're going to have a plus sign here. Those are our voltages. Now, looking at it from the different perspective, all I'm going to do is, since I want that this circuit flipped upside down so that I have positive polarity on top, right? So I'm just going to redraw it really quickly here. So positive polarity on top. So here is V1 of t. Here is my coil L1. The dot was on the positive polarity terminal, so I flipped that upside down, and I'm going to define I1 like so, right? So I1 is flowing from the negative polarity terminal into the undotted terminal. So nothing has changed except that now my voltage is on top because it looks right to me. I'm going to draw my second coil over here. Polarity should be on bottom. excuse me, the dot should be on bottom. Here's V2. I2 was defined like so. So to me, this looks like my dots are on the opposite side configuration, right? So I should have V1 of t is equal to something times, or excuse me, plus or minus L1 di1 by dt, and then m di2 by dt. So let's look at things here. Okay, where's the picture? Here we are. Okay. So we change the plus to minus if I1 is counterclockwise. So is I1 counterclockwise? Yes, because it's flowing in this direction around the loop. So we change the plus sign to minus sign. Change the plus to, or excuse me, change the minus to plus if I2 is clockwise. I2 is counterclockwise, so we leave the minus sign alone. For V2, we're going to have L2 di2 by dt over here, m di1 by dt. So we're expecting a plus sign. We change the plus to minus if I2 is, I write that incorrectly. I did. So that's a problem. This one right here, I apologize for that. It's supposed to be clockwise. So my mistake there. I wrote it incorrectly in my notes as well, so I'll need to fix that. I'm glad I had the textbook open. So I2 is counterclockwise. So this gets a plus sign. Change our minus to plus if I1 is counterclockwise. I1 is counterclockwise, so this gets a plus sign. We get the exact same results as we got working it the other way when I fixed the picture, so I apologize for that. But so I just want to be clear, you should be able to do literally any of these, either by one method or the other, or both. They represent the exact same thing, just from a slightly different perspective, okay? So let's do as Bailey asked and work a problem with numbers. So let's say that I have the following circuit. I have some source voltage. Here I am going to have a 5 ohm resistor. This is going to be a 10 microfarad capacitor. This is going to be a 1 millihenry inductor, dotted terminal on top. On this side, I'm going to have a 3 millihenry inductor, dotted terminal on top. I have another 10 microfarad capacitor. I have a resistance here of 20 ohms. And what I want to determine is this current flowing through my load resistor. So I'm going to call this IL of T for this system. And the mutual inductance coupling these two circuits together is 0.5 millihenry. Okay. So this is what our circuit looks like in the time domain. Let me tell you explicitly here that Vs of t is 10 cosine 2 pi times 10 to the 3 t volts. Okay. So we are very much not going to work this circuit in the time domain. Okay, we're going to work it in the frequency domain like we had done previously. But before we do that, I want to do a couple of things. Okay, so I want you guys to tell me what polarity I should use for the voltage drop across the 1 millihenry inductor. Positive on top or positive on bottom? Positive on top, okay. So I'm going to call this voltage V1 of t. What about for the 3 millihenry inductor on the right-hand side of the circuit? Positive on top or positive on bottom? Pick one. Positive on top, okay? We're going to wind up doing mesh here, or I'll call it mesh, but do I want my current for the left-hand loop to be clockwise or counterclockwise? Clockwise, okay. Do I want the current for the right-hand loop to be clockwise or counterclockwise? IL is given, but we can choose I2 to be whatever we want. Do you want it clockwise or counterclockwise? Do you want it to be in the same direction as IL or the opposite direction as IL? It literally doesn't matter. You're just making a choice. So you said opposite, so let's do opposite. Okay. So the reason why I'm doing this, we're going to wind up doing KVL around both of these loops. And so I'm going to go ahead and define what those time domain voltages are, and then we're going to convert them into the frequency domain here in a moment. Okay. So we know that V1 of t will be plus or minus L1 di1 of t by dt plus or minus m di2 by dt. And we know that V2 will be L2 plus or minus L2 di2 by dt plus or minus m di1 by dt. So what signs should these things get? I believe they will all be positive. So let's talk about what these are going to look like in the frequency domain, right? So I'm going to have some frequency domain voltage V1, and I'm going to have some frequency domain voltage V2. So the voltage drop across my inductor 1 is L1 times the derivative of my current with respect to time. In the frequency domain, the derivative operation is simply multiplying by j omega. We actually talked about that earlier when we went through our frequency domain relationship, right? So that's literally just going to be j omega L times I1 plus j omega m times I2. Excuse me, this should be an L1 here. Similarly, this voltage drop is going to be j omega L2 I2 plus j omega m times I1. So anytime we do a derivative in the time domain and we have a steady state sinusoidal circuit, it's the same as just multiplying by j omega. So are we okay with how we're going to represent those particular voltages in the frequency domain? Nobody is threatening to beat me up in the parking lot, so I feel like we're all okay-ish. So I wanted to be explicit about that because we're going to analyze this circuit here in the frequency domain in a minute, and we're going to have to do it a little bit differently than we would have done it before we understood or introduced the concept of mutual inductance, because we can no longer just say it's j omega L times I for the voltage drop across the inductor, because there's that mutual term too, okay? So I've explicitly figured out what those voltage drops are going to look like when I write my KVL equations. So now let's talk about what this circuit looks like in the frequency domain, okay? So my voltage source is going to look like a phasor voltage now, right? So what's that phasor voltage going to be? How do I convert this from the time domain to the frequency domain? I understand it's been a couple of weeks, but I feel like we should be able to do it. So the 2 pi times 10 to the 3 is the omega. The phase angle there is 0, right? It's 2 pi times 10 to the 3 t plus 0 degrees, right? So 10 angle 0 degrees. So we have 10 angle 0 degrees volts there. What's the impedance of my resistor going to look like? Five ohms. The impedance of a resistor is just the resistor value. Absolutely right. What is the, I'm going to move this down because I'm about to run into my previous writing. Sorry about this. What's the impedance of my capacitor going to be? Let's scroll up here so you can see it. So negative J divided by what? Omega C, absolutely right. So negative 1I divided, nope, that's how I wanted to do it. Negative 1I. Omega is 2 pi times 10 to the 3. And C is 10 times 10 to the minus 6. I get that to be minus J 15.915 ohms. You guys feel free to verify that in your calculator if you want to. What about my inductor L1? What's that impedance going to be? J omega L, okay. So 1I times 2 pi times 10 to the positive 3. And then L was 1 millihenry, so 1 times 10 to the minus 3. So that looks like J 2 pi ohms. I'm going to leave it like that just for the sake of argument. So over here, I'm going to have my other inductor. So it's 3 millihenries, so it should be 3 times larger. So that's going to look like J6 ohms. The capacitor had the same value, so that's going to look like minus J 15.915 ohms. My resistor over here was 20 ohms. Oops, I don't know what the heck just happened. Here is the phasor current IL. And what's our mutual inductance going to look like in the frequency domain? So it's half a millihenry, which means it has half the impedance of that inductor L1. So it's just going to look like pi, J pi ohms. Sorry, you're absolutely right. J6 pi. Oh, thank you. I forgot that. So thank you very much. Okay. Now, just to be clear here, this is the direction that we've defined our current I1 in. This is the direction that we have defined our current I2 in. This is how we found V1, and this is how we found V2. So now what I'm going to do is I'm going to write a KVL equation around mesh 1. Right. So I'm going to have negative 10 angle 0 degree volts plus 5 minus J 15.915 ohms times I1 plus V1 is equal to 0. And now I'm going to substitute in that V1 that we did earlier, right? Where this J omega L1 right here is just that J2 pi ohms. And this J omega M is J pi ohms. So this is still the same equation. I'm just substituting in that thing. So I'm going to have 5 minus J 15.915 plus J 2 pi, all of that added together, times I1 plus J pi ohms times I2 is equal to 0. Is everybody okay with what I've done there? I've just lumped all of those impedances that I1 sees together as one single thing, and then the only impedance, which is the mutual inductance part seen by I2, gets multiplied by I2. If you're not catching what I'm throwing, let me know and I will try to explain it better or ask what's what. All right, nobody's saying anything, so let's leave it. Let's leave well enough on. Okay. Now we're going to do KVL. At mesh 2. Right. I'm going to follow I2 around its path. So I'm going to see 20 minus J 15.915 ohms times I2 plus B2 is equal to 0. And now I'm simply going to substitute in V2, right? So we found out that J omega L2 was 6 pi times J ohms, and J omega M, once again, was J times pi ohms. So that means we're going to have 20 minus J 15.915 plus J 6 pi ohms, all times I2 plus J times pi ohms times I1 is equal to 0. And now we have to solve this system of equations. Because it's a system using complex numbers, that's a MathCAD problem. So let's go ahead and do it using MathCAD. Taking longer than I want it to open up, but that'll be okay. All right, so I'm going to use a solve block. I'm going to define I1 as 1 angle 0 degrees amps, and I2 as 1 angle 0 degrees amps. And now I'm just going to put in my equations, right? So I have negative, that is not a negative sign, 10 angle 0 degrees volts plus 5 ohms minus 1J times 1J times 15 point, what do we get for the capacitor? 15.915, all right. Plus 1J times 2 pi ohms. That gets multiplied by I1 plus 1J times pi times ohms. That gets multiplied by I2. Set that equal to 0. So does that look correct for my first equation? Did I mess any numbers up or anything? All right. For my second equation, I have 20 ohms minus J times 15.915 ohms plus J times 6 pi ohms times I2 plus J times pi ohms times I1 equal to 0. And now I'm going to solve this thing, giving myself a matrix here. So I1 and I2, find I1 and I2. Express these as polar form complex numbers. like so. And the IL that we are trying to find is just negative I2. So I get to be 0.139 amps with an angle of 142.182 degrees. So it's not hugely different than what we did for that first section of class where we were simply analyzing circuits in the frequency domain. The hiccup here comes from the fact that we have to remember to include the mutual terms, and we have to make sure that we get the signs right on both the self-induced part and the mutually induced part of both voltages, or everything's going to go wrong, right? So applying those rules to figure out whether or not those bits get plus signs or minus signs is legitimately the hardest part of any of this stuff. Everything else is stuff that we've done before. Okay. So we only have 15 minutes left of class. I don't think that's enough time for me to work another example. So we're going to stop here for today, and we'll probably spend the first half of the next class meeting or so working a few more of these problems, and I'll try to get you guys a homework set up on it as well. Actually, let's just say our next class meeting is just going to be working more examples and in-class assignment and homework stuff. Okay. All right. Thank you guys for your time. I will see you on next Tuesday.